Hi, Calculus. We're going to be looking at related rates today. Things that are growing in different directions and that sort of thing, and it follows from our implicit differentiation. So I have one that's kind of a fill in the blank just to get us started, but we have a raindrop falling into a puddle and ripples spread. So the radius is going to be growing, the area is going to be growing, the circumference is going to be growing. So we've got a lot of things going on at the same time. So if you were to see the expression dr by dt, we are talking about the change of the radius with respect to time. The radius is changing with respect to time. The rate of change of the circumference with respect to time can be written as dc dt, just to get used to our notation. And lastly, the rate of change of the area with respect to time can be written as dA dt. So we are looking for the rate of increase of the circumference of one of the circles. So we need to start with a formula that we know for what it is that we're looking for change of. So circumference is 2 pi r. So if we're going to take the derivative of both sides, because we're looking for a rate of change, we're going to be doing what we did yesterday. So I'm going to take the derivative of both sides with respect to time. With respect to time, both sides. So my next line would be dc dt equals d 2 pi r dt. Okay, so let's do that. dc dt equals the derivative of 2 pi r with respect to time is, well, the derivative of 2 pi r is 2 pi, but don't forget the guts because the letters don't match, dr dt. So that is an expression that we have, and we were told in the question that the rate of change of the circle, the radius, grows at a rate of 3 centimeters per second. So we know dr dt. dr dt is growth, so it's positive, and it's 3. So dc dt is 2 pi times 3. So it's growing at a rate of 6 pi centimeters per second. This is 2 pi times the rate of change of the radius with respect to time. And so it is changing at 6 pi centimeters per second. Okay, let's look at the next part. Find the rate of increase of the area of one circle. So we have to start with what it is we're looking for the rate of change about, and it's pi r squared would be our starting place. We're going to take the derivative of both sides with respect to time because we're looking for a rate of change. So it would be dA dt equals d blah 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 dt. dA dt is, okay, what is this derivative? Well, the derivative of pi r squared would be 2 pi r, but don't forget the guts because r and t don't match, dr dt. And we know dr dt is 3, so it would be 2 pi r times 3, which would be 6 pi r. This rate of change is dependent upon the area. This is 2 pi r times the rate of change of the radius with respect to time. Therefore, the area is changing at a rate of 6 pi r centimeters squared per second. So it's a different rate depending on what the radius is at that moment. Continuing with that thought, we want to know the rate of increase of the area of the circle that has an area of 81 pi centimeters squared. So I know the rate of change with respect to r, but I need to know when that is specifically. So when the area is 81 pi. I know area is pi r squared. When is it 81 pi? That happens when r is 9. Negative 9 doesn't need to be considered because it doesn't make sense. So at that moment, dA dt equals 6 pi times the radius at that moment would be 54 pi centimeters squared per second. Another type of related rate question could be a change of distance, so things are moving. We have Ben and Evan start from Listowel and drive along perpendicular roads. Ben drives at a speed of 45 kilometers an hour as he heads towards Palmerston. And Evan travels at a speed of 40 kilometers an hour. And Evan begins 1 hour before Ben. At what rate are their cars separating 3 hours after Evan leaves? So there's a lot of extra information here. It would not be a bad idea to define our variables and write down what it is that we know. So looking at it the way I drew it, I would choose x to be Ben's distance. Kind of stuck with my x's and y's. In kilometers. Okay, I'm going to let y represent Evan's distance in kilometers. And I'm going to let r represent the distance between them. So that gets me started, and then I am going to write down what is it that I know. So I know the rate of change of Ben. I know that he is driving 45 kilometers an hour, so I know dx dt. It is 45. Okay. I know the rate of change of Evan. That's dy dt, and it is 40 kilometers an hour, kilometers an hour. Okay, what else do I know? I know some distances, sorry. Okay, so Evan begins 1 hour before Ben, and he has gone 3 hours. So if Ben has gone 3 hours, he has traveled 120 kilometers. So I know how far he has traveled. And Ben waited an hour, and then he drove for 2 hours, so he drove a total of 90 kilometers. So that could be helpful as well. All right, let's get started. First of all, like the last example, I needed to start with an equation I know about the relationship of what's going on in the story. And the relationship here is a Pythagorean theorem relationship, because we've got things all perpendicular. Isn't that lovely? So I know that x squared plus y squared equals r squared is the relationship I know. Last time it was area, and so on. Then I'm going to take the derivative of both sides because we're talking about related rates and we want to see how things are changing. So if I take the derivative of both sides, you don't have to show this line, but it's not a bad strategy. I'm taking the derivative with respect to t of everything. That's a related rate. Take the derivative with respect to time of both sides. All right, here we go. The derivative of the first piece is, the derivative of x squared is 2x. But I'm not taking the derivative with respect to x. The letters don't match, so don't forget the guts. 2x dx dt. Plus, I'm taking the derivative of y squared with respect to t. So it's 2y. Don't forget the guts. I'm taking the derivative of r squared with respect to t, to r dr dt. It's probably not a bad idea before we tidy anything up to put in what we know. I know dx dt is 45. I know that Ben has traveled in the x direction 90, and there was a 2, plus. I know the distance that, I'm getting my students mixed up here, Evan. It was, nope, he did 120. He's going very slow though. 120, and his rate of change was 40. So I know all of these values. At the moment that they are 120 and 90 apart, I should be able to figure out that distance. I just haven't done so yet. And dr dt is what I am looking to find. So that's what I want, and I just have a little bit of work to get that guy. To get that missing piece, I'm using the same relationship as the one that I started with, x squared plus y squared equals r squared. So that little bit of work that I need to do is 90 squared plus 120 squared equals, and I get a value of 150. All right, dr dt. I've got to isolate for dr dt. So basically I've got 90 times 90, which is 8100. And I've got 80 times 120, because I always do things out of order, 9600. And I'm going to divide that left side by 300 to get dr dt. I am cheating a little bit here. I am getting 59 kilometers an hour. They are separating at 59 kilometers an hour at the moment that they are 120 and 90 kilometers apart.